Welcome to these gentle, soothing stories for sleep. I'm so glad you are here. Whether you are preparing to drift off to sleep, relaxing after a long day, or simply seeking a quiet companion, you've come to the right place. Tonight, we begin a journey into one of humanity's oldest and most profound dreams, exploring the question, evolving to fly, could humans make it happen? Before we begin, I'd love to know where you're listening from tonight, or how your day was. Please leave a comment below. Wherever you are, I hope you are feeling comfortable, relaxed, and ready to explore something gentle yet extraordinary. And if you find these soothing scientific journeys interesting, pleasant, or even just wonderfully weird, please consider liking this video and subscribing to the channel. It helps more souls who are searching for peace find their way here. Have you ever felt it? That sensation in a dream, the sudden, heart-stopping lurch of a fall from a great height, a plummet through an endless velvet darkness that feels so real your muscles twitch in bed. But then, just as the ground rushes up to meet you, something miraculous happens. The terror gives way to a strange and sudden control. You pull up, you extend your arms, and the horrifying descent curves into a graceful, effortless glide. You are flying. The city below becomes a silent, sleeping map of soft lights and deep shadows. The forests, a plush, dark carpet under a silver moon. There is no sound of wind, no strain of muscle, just a perfect, weightless freedom as you soar through the cool night air, unbound and utterly serene. It is a dream so common, so deeply woven into the fabric of our sleeping lives, that it feels less like a fantasy and more like a forgotten memory. We wake from it with a sigh, a faint sense of loss, feeling the familiar, unshakable heaviness of our bodies in our beds, the constant and gentle pressure that reminds us we belong to the world below. This feeling, this ever-present companion from the moment we are born to the moment we die, is the first great barrier to our dream. It is the weight of the world, gravity. We often think of it as a force that pulls us down, but it is more intimate than that. The great scientist Isaac Newton realized that it is a mutual attraction, an invisible, unbreakable tether stretching between every single particle of your body and every single particle of the earth. It is a constant, silent embrace, connecting you to the very core of the planet. Imagine you are standing, not on the surface of the world, but at the bottom of a deep and tranquil ocean, an ocean of force. The deeper you are, the greater the pressure. We live our entire lives at the bottom of this gravitational well, and our bodies are exquisitely sculpted by its influence. Our very design is a testament to life under the full, loving pressure of 1G. Our bones are solid, thick, and filled with dense marrow, acting as powerful pillars to support our weight. Our leg muscles, our glutes, and the powerful muscles of our back are the largest and strongest in our bodies, all dedicated to the simple, miraculous act of standing upright and walking upon the land. We are magnificent terrestrial creatures, built to stride, to run, to climb, but fundamentally to be held by the earth. This grounded architecture of our bodies reveals a fundamental law of nature that stands as another immense hurdle to flight for a creature of our size, a principle known as the square cube law. It sounds complex, but it is a beautifully simple idea. As an object gets bigger, its volume, and therefore its mass and weight, increases with the cube of its dimensions. That means if you double its size, its weight increases eightfold. But its surface area, or in the case of our bones and muscles, their cross-sectional strength, only increases by the square. It only gets 4 times stronger. A tiny ant can carry many times its own weight, because its strength is immense relative to its tiny mass. But if you were to scale that same ant up to the size of an elephant, it would collapse into a heap, its own legs shattering under its impossible weight. This law is the quiet tyrant of biology, dictating the shape and scale of all life. It is why insects can be so varied and strange, and why large animals are all constrained to a few basic, robust designs. And it is why a 6-foot, 80-kilogram human, so perfectly adapted to life on the ground, represents a monumental challenge for the physics of flight. The dream of soaring is a dream of weightlessness, a fantasy of severing that tether to the world. But to achieve it, We cannot wish gravity away. Instead, we must find a way to master a different kind of invisible ocean, the one that fills the space between everything. Our dreams may be weightless, but the air itself is not. It has substance, shape, and power. To fly, we must first understand the invisible river we wish to swim in, the very architecture of the sky that waits above. Think of the last time you felt the wind on your face, a force that is undeniably real, a push you can lean into, a caress you can feel, yet a substance you cannot see. It is the ghost of a presence, the breath of the world itself. We tend to think of the air as emptiness, a void that we move through, but it is a place, as real and as physical as the ocean. If we could attune our senses, we could perceive its subtle landscape, its currents and eddies, its deep and shifting tides. We could smell the approach of rain on a current of air, the scent of wet earth and ozone carried for miles. We could feel the subtle shift in pressure in our ears as the weather changes, a sign of the immense weight of the column of air stretching from our heads all the way to the edge of space. In a quiet, sunlit room, we could watch the lazy dance of dust motes, tiny specks of matter suspended and carried by invisible currents, revealing the air's slow, gentle movement. This substance, this sea of nitrogen and oxygen and countless other molecules, is a fluid. It flows and behaves much like water, only it is thousands of times less dense and far more compressible. To a bird, or to an airplane, the air is not empty space. It is a thick, supportive medium that can be shaped, carved, and leaned upon to hold them aloft. The secret to this support lies in a simple, elegant principle of physics, discovered by a scientist named Daniel Bernoulli. The principle, at its heart, is about a trade-off between speed and pressure. Where a fluid is moving quickly, it exerts less pressure. The wing of a bird or an airplane is a marvel of engineering called an airfoil, and it is perfectly shaped to exploit this rule. It is gently curved on top and flatter on the bottom. As the wing moves forward, it splits the airflow. The air that travels over the longer, curved top surface must speed up to meet the air travelling along the shorter, flatter bottom surface at the back edge of the wing. This means the air is moving faster over the top of the wing, and therefore it is exerting less pressure. The slower moving air beneath the wing exerts a higher pressure. This simple difference, this gentle but persistent push from the higher pressure below, creates an upward force. It is called lift. You have felt this principle in your own life, perhaps without realizing it. It's the same force that makes a shower curtain pull inwards when the water is running, as the moving air and water inside the shower create a zone of lower pressure. It is the same force that makes a spinning ball curve through the air. Lift is the miracle that overcomes the crushing weight of gravity, but it is only one part of a delicate, four-way balancing act. There is weight, the constant pull of gravity. There is lift, the upward force generated by the wings. Then there is thrust, the forward push that keeps the air flowing over the wings, generated by a bird's flapping or a plane's engines. And finally, there is drag, the constant, sticky resistance of the air itself, the friction that tries to slow everything down. Flight is a continuous, graceful dance between these four invisible forces, a constant series of minute adjustments to stay in a perfect state of equilibrium. We spend our entire lives immersed in this fluid, this tangible substance, breathing it, feeling it, moving through it with every step. And yet we are so rarely aware of its profound presence. We are like fish who have never considered the nature of water. We look up at a soaring hawk and see magic, but what we are truly witnessing is a creature that has mastered the physics of its own element. The air is both the obstacle and the medium, the cage and the key. To master this invisible architecture, a body must be more than just willing. It must be perfectly designed, from its very core. The journey to the sky begins not with a leap, but with the very framework of our being, the silent, hidden scaffolding of our bones. Imagine, just for a moment, that you are holding in one hand the complete skeleton of a golden eagle, a magnificent bird of prey with a wingspan that could stretch across a wide room. In your other hand, you hold the skeleton of a common house cat of roughly the same size. The cat's skeleton would feel substantial, solid, with a familiar and reassuring heft. But the eagle's skeleton would feel like a trick, an illusion. It would be impossibly, fantastically light, as if it were spun from dried reeds or balsa wood. This profound lack of weight is not a sign of fragility, but a mark of breathtakingly efficient design, the first and most fundamental adaptation for a life spent in the air. To build a creature that can fly, evolution first had to solve the problem of its own heavy building materials. It had to learn how to sculpt a skeleton, not of solid earth, but of cloud and air. If you could look inside the bone of a bird, you would not find the dense, heavy, marrow-filled structure that we possess. Instead, you would find a hollow space, crisscrossed with a delicate, intricate network of struts and trusses, like the vaulted ceiling of a cathedral or the geodesic dome of a futuristic building. This architectural marvel is called a pneumatized bone, from the ancient Greek word for breath, pneuma. These bones are not just empty. They are filled with air, connected directly to the bird's respiratory system through a series of tiny air sacs. This hollowing out dramatically reduces the weight of the skeleton without compromising its strength. The skeleton of a frigate bird, a master of the ocean winds with a 7-foot wingspan, can weigh less than its own feathers. It is a body that is, in a very real sense, inflated. But lightness is only half of the equation. A flying machine also needs to be rigid. It cannot twist and bend with the powerful forces exerted during flight. To solve this, evolution fused a bird's bones together, creating a solid and unyielding airframe. In a bird's spine, many of the vertebrae are locked into a single, stiff structure. The bones of its hand are fused to create a powerful, blade-like support for the primary flight feathers. And at its tail, the final vertebrae are fused into a structure called a pygostyle, which acts as a lightweight anchor for the tail feathers used for steering. Even the iconic wishbone, or furcula, is a fusion of the two collarbones, acting as a powerful, spring-like strut that helps brace the wings during the powerful downstroke. To achieve this, birds have given up many things. They have no teeth, trading a heavy jaw for a lightweight beak. They have sacrificed the manipulative dexterity of a 5-fingered hand for the aerodynamic perfection of a wing. Our own human skeleton is a beautiful contrast, a story written for a different purpose. Our bones are solid and heavy because they are our load-bearing columns. They are filled with dense marrow that acts as a factory for our blood cells, a luxury a bird cannot afford. Our spine is a flexible column of individual vertebrae, allowing us to bend and twist. Our hands, with their precious, opposable thumbs, are masterpieces of manipulation, capable of the most delicate and creative tasks. We are built to be heavy, to be strong, to be firmly planted upon the ground that supports us. Nature's engineering reveals a profound lesson. To reach the sky, a creature must first hollow itself out, letting go of its own density to become a vessel of air. It is a surrender of weight, a trade of earthly substance for ethereal freedom. But this feather-light frame, this masterpiece of hollowed strength, is nothing but a kite without a string, a sail without the wind. It is a passive structure, waiting to be animated by an engine of immense and singular power. What kind of muscle, what kind of living engine, could possibly move such a structure with enough speed and force to overcome the relentless pull of the earth? You have heard it in every city in the world, that sudden, startling sound. A pigeon, pecking calmly on the pavement one moment, explodes into the air the next. It is not a gentle ascent, it is a concussion of sound and force, the percussive whump, whump, whump of wings beating against the air with incredible power. In that single moment of takeoff, the bird generates more raw power relative to its size than almost any other animal on the planet. This explosive energy comes from an engine of living flesh, a muscular system so specialized and so dominant that it defines the very shape of the bird's body. If you could see beneath the feathers, you would find that the breast of a bird is almost entirely composed of muscle, deep, wine-red tissue, packed with the potential for immense power. These are the pectoral muscles, the engine of sinew that drives the wings. In a strong flying bird, like that city pigeon or a swift, These flight muscles can account for up to 35% of its entire body weight. 1/3 of the animal is pure engine. Compare this to our own bodies. Our pectoral muscles are relatively small, designed for pulling and pushing our arms. Our most powerful muscles are in our legs and our glutes, the engines that carry us across the land. Our entire anatomy is focused downward, on our connection with the ground. A bird's anatomy is focused forward and upward, on its engagement with the air. This incredible engine is composed of highly specialized muscle fibers, tuned for different kinds of flight. Some birds, like chickens or pheasants that only fly in short, explosive bursts to escape danger, have breast meat that is pale and white. This is made of fast-twitch muscle fibers, which can contract incredibly quickly for short periods, but fatigue just as fast. They are built for the sprint. Soaring birds, like the albatross that can stay aloft for days on end, have flight muscles that are dark, almost black with blood. This is slow-twitch muscle, rich in a protein called myoglobin that stores oxygen. These fibers are built for endurance, for the marathon, contracting slowly and steadily for hours or even days without tiring. But perhaps the most elegant secret of this avian engine is not its size or its power, but its ingenious mechanical arrangement. The powerful downstroke of the wing, the stroke that generates most of the lift, is easy to understand. It is pulled down by the massive pectoralis muscle on the breast, just as we might pull a lever downwards. But the upstroke, the recovery stroke, presents a challenge. If the muscle to lift the wing were placed on the bird's back, it would make the creature top-heavy and unstable in the air. Evolution's solution is a work of biomechanical genius. The muscle that powers the upstroke, the supracoracoideus, is also located on the breast, underneath the main pectoral muscle. From this muscle, a long, strong tendon loops up and over the shoulder joint, threading through a natural pulley formed by the bones, and attaches to the top of the wing. When this smaller muscle contracts, it pulls the tendon, and like a rope being pulled through a pulley, it hoists the wing upwards from below. This keeps the bird's center of gravity low and stable, a perfect design for aerial balance. The body of a bird is not a collection of separate parts. It is a single, unified, integrated machine for flight. Every bone, every feather, and every single muscle fiber is tuned for this one, all-consuming purpose. It is an engine of breathtaking efficiency, but such a powerful engine demands an equally incredible amount of fuel. It must burn hotter and faster than any engine we possess within our own bodies. How could a living creature possibly sustain such a ravenous and constant fire within? Consider the hummingbird, a creature that seems to defy the normal flow of time. It hangs in the air with a frantic, vibrating stillness. Its wings a transparent blur, a living jewel suspended by an invisible thread. This tiny body, weighing no more than a coin, is a testament to life lived at the very peak of intensity. It is a biological furnace, an internal engine burning at a rate that is almost incomprehensible to us. Its existence is a constant, desperate race against an energy deficit that is never more than a few hours away. To maintain its aerial dance, a hummingbird must consume its own body weight in nectar every single day. If we were to scale that up, a human with a hummingbird's metabolism would need to consume over 150 pounds of sugar daily, an amount so vast it would kill us almost instantly. This is because the price of flight is a colossal expenditure of energy, and to pay that price, a bird's entire body has been re-engineered to be a ruthlessly efficient furnace. To feel what this is like, imagine a body that is always warm to the touch, a core temperature that hovers around 40 degrees Celsius, or 105 degrees Fahrenheit, a level that for us would be a life-threatening fever. Picture a world seen not through eyes of leisure, but through the desperate eyes of an animal that must find fuel, and find it constantly. Flowers are not objects of passive beauty. They are vital fueling stations, each containing a precious droplet of the high-octane sugar needed to keep the fire from going out. This internal inferno is known as an organism's metabolism, the sum of all the chemical reactions that convert food into energy. Birds, especially small, flying birds, have the highest metabolic rates of any vertebrate on the planet. Their cells burn through fuel sugars, fats, and proteins at a breathtaking pace, to generate the massive quantities of a molecule called ATP, the universal energy currency of life. This energy is what powers the contraction of their immense flight muscles. To feed this furnace, their digestive systems are models of brutal efficiency. Food is processed, and nutrients are stripped out with incredible speed. There is no time for leisurely digestion. Any excess weight is a penalty in the air, so waste is expelled as quickly as possible. We, on the other hand, are built on a completely different metabolic principle. Our metabolism is a slow-burning fire, designed for endurance and conservation. Our bodies are masters of storing energy, packing it away as fat in case of lean times. We can survive for days, even weeks, without food. A hummingbird can starve to death in a single night. Its entire life is lived on this razor's edge of energetic balance. To fly is to experience life at a different tempo, a frantic, accelerated rhythm where the world is a blur and every waking moment is a search for the fuel needed to keep going. It is a beautiful, dazzling, but ultimately brutal existence, a life of constant consumption to power, a life of impossible freedom. A fire this hot, a furnace burning with such intensity, requires a constant and massive supply of one key element. More than food, more than water, it needs oxygen to fuel the combustion. The simple, in and out rhythm of our own breathing, the gentle tide of our lungs, would be wholly and utterly inadequate for the task. It would be like trying to cool a blast furnace with a single, gentle breath. Take a deep breath. Feel your chest rise as your lungs fill with air, and then feel it fall as they empty. It is a simple, beautiful rhythm, a tidal flow of filling and emptying that has sustained you for your entire life. Now, imagine that the breath never had to stop. Imagine that fresh, clean, oxygen-rich air was not something you took in, but something that flowed through you, a constant, uninterrupted river of life. This is not a fantasy. It is the reality of how a bird breathes. It is a system so efficient, so perfectly designed for extracting oxygen from the air, that it allows them to fly in places where we could not even walk. It is the secret that allows a goose to soar over the highest peaks of the Himalayas. If you could see inside a bird's body, you would find a system unlike anything in our own. Beyond the lungs themselves, there is a series of delicate, interconnected balloons called air sacs. These sacs fill much of the body cavity, extending into the spaces between the organs, and even reaching deep into the hollows of the major bones. They don't absorb oxygen themselves. Instead, they act as bellows, storing air and ensuring that it flows through the lungs in a single direction, like a river that never changes its course. This one-way, or unidirectional, flow is the key. In our own tidal breathing, we inhale fresh air into our lungs, and then we exhale the used, carbon dioxide-rich air back out the same way. The result is that fresh air and stale air are constantly mixing, and our lungs are never at their peak oxygen capacity. A bird's system elegantly solves this problem with a two-breath cycle. When a bird first inhales, the fresh air doesn't go straight to the lungs. Instead, it is drawn into the posterior air sacs, near the back of the body. When the bird then exhales for the first time, it pushes this fresh air from the posterior sacs into the lungs. Now, when the bird inhales for the second time, it draws a new breath of fresh air into those same posterior sacs, and at the same time, it pulls the now used air out of its lungs and into the anterior air sacs at the front of its body. Finally, with the second exhalation, the stale air from the anterior sacs is expelled, and the fresh air that was in the lungs is moved into the anterior sacs, ready to be expelled on the next breath. It sounds complex, but the result is beautifully simple. The lungs are almost continuously bathed in a stream of fresh, high-oxygen air, both during inhalation and exhalation. There is no mixing of good air and bad. This is what gives birds the ability to perform incredible feats of endurance at high altitudes. The bar-headed goose, for example, migrates over the Himalayas at altitudes of nearly 9,000 meters, or almost 29,000 feet, where the air is so thin that a human would lose consciousness from hypoxia within minutes. They can do this because their respiratory system is so profoundly efficient at extracting every possible molecule of oxygen from the sparse mountain air. The act of breathing, for us, is a constant rhythm of filling and emptying, a cycle of presence and absence. For a bird, it is a constant state of being filled, a continuous and unbroken connection to the life-giving air around it. It is a profound difference in the very experience of being alive. This river of pure oxygen must then be captured and transported with incredible speed and efficiency to the furious, demanding engine of the muscles. This requires a circulatory system of truly exceptional power, driven by a heart that beats to the frantic drumbeat of the sky. Think of the last time you truly exerted yourself, perhaps sprinting for a bus or climbing a steep flight of stairs. You can feel your heart in your chest, a frantic, pounding drumbeat, a powerful reminder of the engine that drives you. Now, imagine that frantic pace as your calm, quiet, resting state. Imagine a heart that lives its entire life at the very peak of what yours can achieve, and then doubles it, and doubles it again. This is the heart of a bird. It is the relentless, unwavering drumbeat of the sky, an organ of such profound power and endurance that it makes our own steady rhythm seem like a leisurely stroll. If you could place your ear against the feathered breast of a tiny songbird, you would not hear a simple, percussive thump-thump. The sound would be a continuous, high-frequency vibration, a hum of vitality so rapid that the individual beats merge into a single, sustained note of life. This incredible organ is the core of the circulatory system, the distribution network that takes the oxygen gathered by the hyper-efficient lungs and delivers it to the furnace of the muscles. Like us, birds possess a highly advanced four-chambered heart. This design is one of nature's great innovations, a double pump system that keeps oxygenated blood, returning fresh from the lungs, completely separate from the deoxygenated blood returning from the body. It ensures that the muscles receive a supply of blood that is as rich in oxygen as it can possibly be. But while the basic design is the same, the performance is on an entirely different level. A bird's heart is, relative to its body size, a monster. It is significantly larger and more powerful than a mammal's heart of a comparable size. A hummingbird's heart, that tiny, perfect engine, can make up nearly 2.5% of its total body weight. Our own human heart, by contrast, accounts for less than 0.5% of our weight. This larger size allows it to pump a much greater volume of blood with every single beat, and the number of beats is simply staggering. That same hummingbird, while hovering in the air, can have a heart rate of over 1,200 beats per minute. That is 20 beats every single second. Even a sparrow at rest has a heart rate of around 500 beats per minute, a pace our own bodies could not sustain for more than a few moments. This furious pump generates a much higher blood pressure than we experience, forcing the blood through the arteries and veins at incredible speed, ensuring that the supply of oxygen to those massive flight muscles is constant and immediate. The blood itself is also adapted for this high-speed delivery, with specialized hemoglobin that can capture and release oxygen more efficiently. The heart is the drum that sets the rhythm of life, the metronome of our existence. The steady, reliable beat of our own heart speaks of a life designed for persistence, for thought, for endurance on the ground. The frantic, impossibly fast drumbeat of a bird's heart speaks of a life lived at an intensity we can barely comprehend, a life that is a constant, powerful, explosive burst of energy, a life spent on the wing, with the body engineered for flight, the light bones, the powerful muscles, the furious metabolism, the river of air, and the hummingbird heart. What then of the mind? How must the world be perceived when you can move through all three of its dimensions at will, and at such an incredible speed? Look around the room you are in. Notice the floor beneath you, the solid ground that supports you. Notice the walls that define the space. And notice the ceiling above, a surface that represents an impassable boundary, an end to your vertical world. Now, try to imagine that the ceiling is just another floor, a surface you could stand on, launch from, or land upon just as easily as the one beneath your feet. Imagine that every surface, at any orientation, is a potential foothold. In that single shift of perception, the world becomes an entirely different, vastly more complex, and infinitely more liberating place. This is the world a bird inhabits. To us, the world is a series of paths and corridors, a largely two-dimensional map we walk across. To a bird, the world is a volume, a sphere of possibilities to be navigated. This requires not just a different body, but a different kind of mind, a different way of seeing and sensing the very fabric of reality. The journey begins with the eyes. A falcon, soaring high on a thermal, sees the world with a clarity that we can only call supernatural. The landscape below is not a blur, but a perfectly rendered tapestry of textures and patterns. It can spot a mouse, a single, tiny creature, moving through a field of tall grass from over a mile away. This is possible because the retina of a raptor's eye is packed with a much higher density of photoreceptor cells than our own, giving it a visual acuity, a sharpness of vision that is 2 to 3 times greater than that of a human with perfect eyesight. Furthermore, birds see a world that is, in a very real sense, painted with more colors. Their eyes can perceive light into the ultraviolet spectrum, a range of colors completely invisible to us. This ability reveals a hidden layer of information in the world. It makes certain berries and flowers stand out with brilliant, irresistible patterns. It can reveal the trails of urine left by small prey, trails that glow like neon signs in their ultraviolet world. But seeing the world is one thing. Navigating it in 3 dimensions at high speed is another. It requires a profound neurological toolkit. A bird must possess an exquisite sense of proprioception, an innate and instantaneous awareness of where every feather and every part of its body is in space, without having to look. It requires a brain that can perform incredibly complex spatial calculations in fractions of a second, judging speed, trajectory, and distance with pinpoint accuracy. For their incredible long-distance migrations, many birds possess a sense that seems like magic to us: magnetoreception. They can literally feel the Earth's magnetic field, using it as a built-in, infallible global compass to guide them across continents and oceans. The avian brain that processes all of this information is a marvel of efficiency. Though small, it is incredibly dense. The part of their brain responsible for higher cognitive functions, called the dorsal ventricular ridge, is packed with neurons in a way that is far more efficient than the layered structure of our own cerebral cortex. Flight is not merely a physical act. It is a profound neurological feat. To fly would be to unlearn the very grammar of our world. The absolute meanings of up and down, of above and below, would dissolve. Our entire understanding of space, and of our place within that space, would be fundamentally and forever altered. We have now seen the blueprint of a flying creature, a body and mind honed by millions of years to master the sky. We have seen the incredible lightness of its bones, the power of its muscles, the fire of its metabolism, and the sharpness of its senses. Now we must turn and face the most difficult and profound question of all. How does evolution build such a masterpiece? It is a process that is not one of conscious design, but one of magnificent, beautiful, and terrifying chance, acting across an ocean of time. Within every single cell of your body, coiled so tightly it is almost beyond imagination, there is a library. This library contains a story of almost unimaginable length and antiquity, a narrative stretching back not for hundreds, but for thousands of millions of years. It is the complete, unabridged story of your ancestry, a detailed instruction manual for building a human being, passed down from the very first spark of life on this planet. This library is the molecule DNA, and to understand how a wing is built, we must first understand the language in which this epic is written. Let us visualize this molecule not as a static diagram in a textbook, but as a flowing, twisting river of information, a double helix spiraling back through the eons. Each turn of the spiral, each rung of the ladder, is a word, a sentence, a chapter in the great book of life. This river flows from parent to child, from generation to generation, in an unbroken stream. When a new creature is formed, this river of information is read, and the instructions are followed with breathtaking precision, building a heart, a lung, a brain, a body. This is the fundamental blueprint for life. But a blueprint is not just a list of materials. It is a set of instructions about when and where to use them. The secret to life's incredible diversity is not just in having different genes, but in using the same genes in different ways. This process is called gene regulation, and it is like a vast, intricate switchboard within each cell. A single gene might contain the instructions for a protein that makes a bone grow, but the regulators are what tell that gene to turn on in a specific place for a specific amount of time, to build a finger, and to turn on in a different way to build a toe. Among the most important of these switches are the master controllers, a set of genes called the Hox genes. These are the architects of the body plan, the genes that lay out the basic structure, determining where the head will go, where the limbs will sprout, where the tail end of the animal will be. The Hox genes of a fly and the Hox genes of a human are astonishingly similar, a deep echo of our shared ancestry. A tiny tweak in when or where one of these master switches is flipped during development can lead to a dramatic change in the final body, adding a pair of legs or changing the shape of a limb. This is how evolution can produce such dramatic variety from a shared set of tools. But for any change to happen at all, for a new chapter to be written in the book of life, there must be a source of novelty. The river of information must occasionally change its course. The source of this change is mutation. As the DNA is copied, generation after generation, tiny, random errors are sometimes made. A letter of the genetic code, an A, a T, a C, or a G, is accidentally swapped, deleted, or inserted. The process is much like a scribe copying an ancient text by hand. Over thousands of pages, a few small mistakes are inevitable. Most of these mutations are harmless, falling in a non-critical part of the code. Many are harmful, causing a vital protein to fail. But very, very rarely, a copying error produces a trait that is, by sheer chance, advantageous. A slightly denser bone, a slightly more efficient muscle, a feather that is a little bit better at trapping air. This is the seed of all evolutionary change, a random, unguided whisper of possibility. We think of ourselves as solid, stable individuals, but we are, in a deeper sense, merely temporary custodians. We are the vessels for this ancient, immortal river of information that flows through us and will continue its journey long after we are gone, carrying with it the story of our time here. But a random error, a single new word in the book, is not enough to build something as complex as a wing. For that tiny seed of change to grow, it needs a sculptor, a powerful shaping force that can select the useful and discard the useless, acting patiently and relentlessly over eons. Imagine a sculptor standing before a vast, rough block of marble. But this sculptor is blind. He has no image in his mind of the final statue, no grand design he is working towards. His only tool is a simple chisel, and his only guide is a single, simple rule. He taps the block of marble, and wherever he finds a weak spot, a crack, or a flaw, he chips that piece away. He continues this process for an eternity, tapping and chipping, always removing the weakest part of what remains. After millions and millions of years, a beautiful, intricate form begins to emerge from the stone, a shape of grace and strength. It looks as if it were designed with profound intelligence, yet it is merely the result of an unintelligent, relentless process of removing what does not work. This blind sculptor is natural selection, the single most powerful force in the story of life. Let's give this sculptor a real block of stone to work with. Picture an ancient, two-legged dinosaur, a distant ancestor of birds. It is covered not in scales, but in frayed, primitive feathers, which it uses for insulation to keep warm. Within the population of these creatures, there is variation. Due to random mutations, some have feathers that are slightly thicker and denser than others. Now, imagine a sudden, prolonged cold snap grips the environment. The individuals with slightly better insulation are more likely to survive the cold, and therefore more likely to live long enough to reproduce, passing on the genes for their thicker feathers. The environment has, in a sense, selected for that trait. The blind sculptor's chisel has struck, chipping away the individuals who are less suited to the cold. This is the core principle of natural selection, as discovered by Charles Darwin. It has three simple parts. First, there is variation within any population. Second, that variation is heritable, meaning it can be passed down to the next generation. And third, there is differential survival and reproduction. meaning that some variations provide a better chance of surviving and having offspring in a particular environment. Over time, the population will gradually, inevitably, shift to possess more of the advantageous traits. The environment is the artist, and the pressure it exerts is what shapes the clay of life. For flight to evolve, there must have been a consistent environmental pressure that favored any creature that was even a little bit better at getting off the ground. Perhaps it was to escape from larger predators, a theory known as the ground-up model. Or perhaps it was to move more efficiently between trees, gliding from branch to branch, a trees-down model. Whatever the pressure, it must have been relentless. But it is crucial to remember that evolution has no goal. The sculptor does not know he is making a wing. A feather did not originally evolve for flight. Its first purpose was almost certainly for keeping warm, or perhaps for display, to attract a mate. Only later, as it became larger and more aerodynamic, was this existing structure co-opted for a new purpose, a process biologists call exaptation. The first feathered arms that were flapped were not for flying, but perhaps for adding thrust while running up steep slopes, or for maintaining balance. Each tiny, intermediate step must have provided a small, immediate advantage. Evolution does not make investments for a distant future payoff. We look at the wing of an eagle, and we see a machine of perfect, breathtaking design. But it is not the product of a grand, preconceived plan. It is the accidental masterpiece of a blind sculptor, the result of countless trillions of tiny, desperate struggles for survival, a story of life and death, of chance and necessity, written into bone and feather. This process is powerful, patient, and creative. But for it to achieve something as monumental as transforming a terrestrial dinosaur into a master of the air, it requires one final, crucial ingredient, an ingredient so vast that it is almost impossible for the human mind to truly comprehend: the abyss of deep time. Imagine if the entire sprawling history of planet Earth, all 4.5 billion years of it, were compressed into a single calendar year. On this scale, the story begins on January 1st. For many long, silent months, the planet is a barren and hostile place. The first, simplest forms of life, tiny single-celled organisms, do not appear in the vast oceans until sometime in late March. The year progresses through spring and summer with agonizing slowness. Life remains microscopic and simple. It is not until late autumn, into November, that the first complex animals, the first fish and amphibians, begin to emerge. On this calendar, the dinosaurs, those magnificent rulers of the ancient world, do not make their grand entrance until the middle of December. They roam the earth for what seems like an eternity, for the weeks that we would call Christmas. They are still here on December 25th. Then, on the evening of December 26th, a catastrophic asteroid strikes, and in a geological blink of an eye, they are gone. The age of mammals begins in the final days of the year. The entire story of human evolution, from our earliest ape-like ancestors, is a ghost that appears sometime on the evening of December 31st. The whole of recorded human history, every king and queen, every empire risen and fallen, every book written, every pyramid built, flashes by in the final 10 seconds before midnight on New Year's Eve. Your own lifetime is a fraction of a blink in the last tick of the clock. This is the abyss of deep time. It is a scale of existence so vast, so far beyond our everyday experience of minutes and hours, that our minds cannot truly grasp it. We are creatures of the fleeting moment, but evolution is a creature of the eon. The blind sculptor of natural selection works with a patience that is both terrifying and beautiful. The slow transformation from a grounded, two-legged dinosaur into the first true bird, a creature like Archaeopteryx, was a journey that took tens of millions of years. That is a span of time thousands of times longer than the entire existence of our species, Homo sapiens. This immense timescale is necessary because evolution works by the slow, painstaking, gradual accumulation of countless tiny changes. A half-formed wing that is not yet useful for gliding and is too clumsy for running or climbing is a dangerous liability. It is a waste of precious energy. So, each and every intermediate step on the long road to flight must have provided some small, immediate advantage in its own right. a slightly longer feather that offered a bit more insulation, a slightly stronger arm that allowed for a little more stability when scrambling up a tree, a lighter bone that required a little less energy to move. Natural selection is not playing a long game. It is rewarding only what works, right here, right now. We live our lives by the sun and the seasons, by the clock and the calendar. But the universe, and the story of life within it, operates on a timescale that defies our intuition and shatters our sense of importance. To ask evolution to grant us wings is to ask the sculptor to compress an epic poem, millions of years in the writing, into a single, hurried word. The process is too slow, the road too long. But what if the path was already partially paved? What if, buried deep within that ancient library of our DNA, we carry the faint, ancestral echoes of creatures who took to the air long before us? At the very base of your spine, there is a small, curved bone called the coccyx. It serves very little purpose other than as an anchor point for a few minor ligaments. But it is not a new invention. It is the remnant, the faint, anatomical ghost of a tail that our distant, primate ancestors once used for balance as they moved through the trees. Our bodies are living museums, filled with these echoes of a past we have long since left behind. We carry within us the memory of the gills our fish-like ancestors once used to breathe water, replayed every moment in the embryonic development of our throat and ears. To understand what potential for flight might lie sleeping within us, we must trace our own story back, walking down the branches of the great tree of life. If we trace our lineage back past the first primates, past the first shrew-like mammals scurrying at the feet of the dinosaurs, we eventually come to a major fork in the road, a split that occurred over 300 million years ago. This is where our ancestors, the synapsids, diverged from the other great branch of terrestrial life, the sauropsids. This sauropsid branch would go on to produce the lizards, the crocodiles, the dinosaurs, and ultimately, the birds. We are their distant, long-lost cousins. For 300 million years, our two lineages have walked separate paths, sculpted by different pressures, adapted for different lives. And yet, for all that time apart, we still share a common, ancient inheritance. We are all vertebrates, and we are all built from the same fundamental genetic toolkit. The Hox genes, those master architects of the body, are still remarkably similar in a human and a pigeon. The gene that tells a limb to grow during development is fundamentally the same. The difference is in the regulation, in the precise timing and location where those genes are switched on and off, sculpting the final form. The most powerful evidence of this shared ancestry is in the structure of our own arms. A human arm, a bat's wing, a whale's flipper, and a bird's wing may look wildly different on the surface, but they are all variations on a single, ancestral theme. The tetrapod limb, cut them open, and you will find the same basic pattern of bones. One large bone in the upper arm, the humerus. Two bones in the forearm, the radius and the ulna. A collection of small wrist bones, the carpals. And a set of hand and finger bones, the metacarpals and phalanges. This is a structure known as a homologous structure, a sign of shared descent. Evolution is a tinkerer, not an inventor. It rarely creates something entirely new from scratch. Instead, it modifies what is already there, stretching one bone, fusing another, shrinking a third, until a walking leg becomes a grasping hand, or a digging paw becomes a wing. But this history also imposes powerful constraints. Our ancestral body plan, the four-limbed vertebrate blueprint, is written into the deepest syntax of our DNA. To sprout a new, third pair of limbs from our back to serve as wings, like a mythical griffin or an angel, would require a fundamental and radical rewriting of our entire developmental code. It would mean duplicating the entire set of Hox genes that govern limb development, something that is evolutionarily almost impossible. Our only feasible path to flight would be the one taken by the birds and the bats. To modify the limbs we already have, to transform our precious, manipulative hands into wings. Our bodies are museums of natural history, telling the story of the seas we came from and the land we eventually conquered. But the story of the open sky, the freedom of the air, belongs to a different branch of the family, a story our own lineage chose not to write. So, if natural evolution is an impossibly long and constrained road, a path our ancestors turned away from hundreds of millions of years ago, could we, the conscious creatures, the masters of technology, take the sculptor's chisel into our own hands? For billions of years, the story of life has been written by a blind author. The text has been edited by the slow, impersonal forces of random mutation and natural selection. But what if the errors in the great book of life were no longer random? What if the author could suddenly see, and what if the pen were placed, for the first time, into our own hands? This is the new reality we are entering, a world where we are no longer merely characters in the story of evolution, but are becoming its conscious editors. Imagine a laboratory, quiet and sterile. A scientist sits not before a block of marble or a canvas, but before a computer screen. The code on the screen is not written in zeros and ones, but in the 4 letters of life: A, T, C, and G. With a few keystrokes, the scientist locates a specific genetic sequence in the human genome, the sequence that instructs our bones to be dense and heavy. That sequence is highlighted and deleted. In its place, a new sequence is stitched into the code, a sequence carefully borrowed from the genome of a bird, an instruction that whispers, "Be light, be hollow, be filled with air." This is not science fiction. This is the power of a revolutionary technology called CRISPR-Cas9. In its simplest terms, CRISPR acts like a pair of exquisitely precise molecular scissors, guided by a programmable address. It can be sent to any location in the 3 billion letter long human genome, find a specific gene, and make a clean cut. Once the DNA is cut, the cell's natural repair mechanisms can be tricked into using a new piece of DNA, supplied by the scientists, as a template, effectively pasting a new gene into the place of the old one. The potential of such a tool is almost limitless, but the challenge of building a wing reveals the true, staggering complexity of life. There is no single gene for wings. To create a flying human would not be a matter of changing one, or 10, or even 100 genes. It would require the perfectly coordinated, simultaneous editing of thousands of genes. Genes for bone density would need to be changed. Genes that regulate the size and fiber type of our pectoral muscles would need to be rewritten. The genes controlling our entire metabolic system would need to be overhauled to run hotter and faster. We would need to somehow write in the genes for feather production, a complex trait unique to dinosaurs and their descendants. Genes for a 4-chambered heart would need to be modified for greater size and power, and the entire blueprint for our tidal lungs would need to be thrown out and replaced with the instructions for a unidirectional avian respiratory system. Beyond the sheer number, there is another, deeper problem. Genes do not exist in isolation. They are part of a fantastically complex, interconnected web of interactions. A single gene can often influence multiple, seemingly unrelated traits, a phenomenon known as pleiotropy. The gene that might help create lighter bones could, as an unforeseen side effect, interfere with the development of the immune system or alter the chemistry of the brain. The blind sculptor of evolution has the luxury of deep time to work out these bugs. A failed experiment, a hopeful monster with a crippling defect, simply dies out, its flawed genes removed from the river of information. But the conscious sculptor, us, would have to live with our mistakes. In gaining this power, we are like children who have been handed the levers to a starship. We are gaining the power of gods, but do we yet possess the wisdom? And even if we could, one day, write the perfect symphony of genetic code, the music must still be played. The hardware of the body must still be built. How would the most delicate and ancient of construction sites, the cradle of the womb, ever accommodate such a radical and alien blueprint? Within the warm, quiet darkness of the womb, the greatest construction project on Earth begins. A single fertilized cell, no larger than a grain of dust, holds within it the complete architectural plan for a thinking, feeling, breathing human being. In the 9 months that follow, that single cell will divide and divide again, multiplying into trillions of cells that will perform a silent, intricate ballet of becoming. This is the world of developmental biology, where the abstract digital code of DNA is translated into the magnificent, living sculpture of a body. It is a symphony of precisely timed genetic cues, a cascade of signals where cells are told to migrate to new locations, to fold into tubes that will become a heart and a spinal cord, to differentiate into skin and bone and nerve. A sheet of cells puckers and for the first time begins to beat. A life has begun. Any attempt to build a winged human using genetic engineering must confront this delicate and unforgiving process. The final form of an organism is not just a product of its genes, but of the entire developmental pathway it follows, from conception to birth. The environment of the womb, the chemical signals from the mother, the physical constraints of the space itself, are all integral parts of the construction process. Our mammalian gestation is a system that has been fine-tuned over 200 million years to build a terrestrial, placental mammal. It is a life support system perfectly designed to build a creature like us. Now, imagine introducing a new, alien blueprint into this ancient workshop. Imagine a developing fetus that, following its new genetic instructions, begins to form a massive keel bone, the deep, blade-like sternum that anchors the flight muscles. How would this rigid, oversized structure fit within the confines of a human uterus? The new code calls for an avian metabolism, a furnace that demands a colossal amount of energy. How could the mother's body, through the gentle filter of the placenta, possibly provide the unique and massive caloric intake required to fuel such a fire? The entire system of pregnancy and birth is calibrated for a certain kind of creature. To change the creature so radically would be to ask the construction site to build a skyscraper with the tools and materials meant for a small cottage. There is an old idea in genetics known as the hopeful monster. It is the theory that perhaps, once in a very long while, a single, massive mutation could occur, creating a radically new and viable life form in a single generational leap. Most modern biologists, however, have come to believe this is almost impossible. Development is not a simple assembly line where new parts can be easily swapped in. It is a deeply integrated process, where the growth of one part of the body affects the growth of all the others. A hopeful monster, with its strange new appendages and altered organs, would almost certainly not survive its own development, its new parts failing to integrate with its ancient, unmodified systems. The 9 months we spend in the womb are a quiet, unconscious replay of eons of our evolutionary history. To change the final chapter of that story, we would have to find a way to rewrite the entire book, from the very first sentence. But let us, for a moment, suspend our disbelief. Let us imagine we overcome the genetic hurdles, that we solve the profound challenges of development. A human with perfectly formed wings is born. What then? The hardware has been built, but how does one learn to use it? What would it be like to stand at the edge of the world and learn, for the first time, the terrifying grammar of the air? Do you remember learning to ride a bicycle? That period of profound awkwardness, the wobbling, the scraped knees, the frustrating series of failed attempts. Your brain and your body were trying to learn a new language, a new way of balancing and moving through the world. And then, there was that one magical moment where it all clicked. The wobbling ceased, and you were suddenly gliding, propelled by your own power, a feeling of pure, exhilarating freedom. Now, imagine that same learning process, but the ground is 100 meters below you, and the cost of a fall is not a scraped knee, but absolute finality. This is the challenge that would face a newly winged human. It is one thing to possess the hardware for flight. It is another thing entirely to learn the software. Imagine a young person, born with these magnificent, feathered appendages, standing at the edge of a high cliff. The wings do not feel like a natural part of them. They are clumsy, heavy, unfamiliar. The instinct, the desperate human instinct, is to flap them wildly, to beat them against the air like a drowning swimmer splashing in the water. But this achieves nothing but exhaustion. They must unlearn every instinct for survival they possess, and begin to learn the subtle, silent grammar of the air. They must feel the way the slightest tilt of a primary feather changes the flow of wind, the precise angle of attack needed to generate lift without stalling, the gentle, upward push of a thermal, an invisible column of rising air that must be felt, not seen. Our brains are, thankfully, creatures of profound adaptability. The brain's ability to remap and rewire itself in response to new experiences is called neural plasticity. In theory, the human brain could learn to control the fantastically complex musculature of a pair of wings. It could create new neural pathways, new maps of the body, to incorporate these new limbs, just as the brain of a person who has lost a limb can learn to control an advanced, mind-reading prosthetic. But the complexity of flight is far more than just flapping. A pilot of an airplane must understand the concept of the flight envelope, a set of parameters that define the safe limits of an aircraft's performance. A living flyer must master this intuitively. They must learn to feel the edge of a stall, the moment when the wing is tilted too steeply and the smooth airflow breaks away, causing a sudden and catastrophic loss of lift. They must learn the physics of a controlled glide, how to trade altitude for distance with maximum efficiency. They must learn how to bank and turn, how to harness the energy of the atmosphere itself, riding the updrafts created by wind hitting a ridge or the columns of warm air rising from the sun-baked earth. A fledgling bird is guided through this complex curriculum by millions of years of instinct. A fledgling human would be guided only by the cold, unforgiving laws of physics and a deep, primal terror. The cost of failure is the most profound barrier of all. When a human baby is learning to walk, it falls. It falls hundreds, even thousands of times. But the fall is only a few inches, cushioned by a soft diaper, and the result is a small cry, a moment of surprise, and then the process continues. The fear of falling is one of our most deeply ingrained instincts, a survival mechanism essential for a primate species that evolved in trees and on cliffs. To overcome that instinct, to willingly launch oneself into the void and trust that your new, untested limbs will catch you, would require a psychological leap of faith that is almost unimaginable. We are creatures of the ground. Our minds, our fears, our very sense of self are all calibrated for a two-dimensional world. Learning to fly would be less like learning a new skill and more like learning to be a new kind of being entirely. And if we, as a species, were to master it, if we were to take to the skies not in machines, but on our own wings, how would our world and our societies change forever? What does a border look like from 5,000 feet in the air? From that serene altitude, the arbitrary line drawn on a map, the line that men and women have fought and died for, the line that defines nations and separates peoples, simply vanishes. It is an invisible fiction, lost in the seamless, unbroken tapestry of the landscape below. From the sky, the world looks different. It looks whole. This is the new perspective that would await a humanity that had learned to fly. Imagine soaring over a great city at dusk. The frantic, noisy rush of the streets, the cacophony of horns and sirens, the individual dramas of millions of lives, all fade away into a gentle, distant murmur. The flow of traffic on the highways becomes a beautiful, silent river of light, red in one direction, white in the other. The city becomes an abstract pattern, a circuit board of glowing grids and deep shadows. The world below is transformed into a beautiful, silent, and distant object of contemplation. This experience, a profound shift in awareness that comes from seeing the world from a great height, is something astronauts have often described. They call it the overview effect. From the silent sanctuary of space, they see Earth not as a collection of warring nations, but as a single, fragile, and breathtakingly beautiful living system. A tiny blue marble hanging in a vast black void. This perspective can inspire a deep sense of awe, of wonder, and of connection to the planet and to all of humanity. But it could also inspire a sense of profound detachment, a dispassionate alienation from the small, grounded struggles of the world below. A society of flyers might begin to see the world, and the people who walk upon it, as something separate from themselves. This new dimension of movement would shatter the very foundations of our civilization. Borders, as we know them, would become unenforceable and therefore meaningless. The concepts of property and privacy would need to be completely redefined. How do you define the boundaries of your land when people can simply descend from the sky? Cities would be rebuilt, no longer spreading outwards in a two-dimensional sprawl, but growing upwards, with entrances and pathways on every level, becoming great, vertical, three-dimensional ecosystems. And would a new and terrible class structure emerge? A society divided not by wealth or by birth, but by the very dimension in which they live. The flyers and the non-flyers. The people of the air and the people of the earth. The Olympus dwellers and the mortals below. This change would run deeper than just our laws and our cities. It would change our souls. Our entire culture, our art, our music, our myths, our very language, is built upon a terrestrial foundation. We speak of deep roots, of being grounded, of having our feet on the earth. A winged humanity would need a new mythology, a new poetry, a new way of understanding itself. It would be a new species, not just biologically, but culturally and philosophically. We might gain the freedom of the sky, a freedom we have dreamed of since the dawn of our consciousness. But what might we lose? Would we lose our connection to the soil, our intimacy with the small, beautiful details of the terrestrial world? Would we lose our sense of community, our humility, the comforting, grounded reality of walking among our fellow human beings? There may be another path. A path that does not require us to rewrite our ancient biology or shatter our societies. What if we do not need to change our bodies, but simply augment them? A different, and perhaps more human, kind of evolution. Listen, for a moment, to the sounds of our modern world. In the gentle hum that sometimes drifts through an open window, you might hear it. The sound of a small drone, its electric motors whining as it hangs in the air, a mechanical bird navigating our city skies. This sound is a quiet prophecy, a hint of a different path to the heavens. A path that does not require the rewriting of our biology, but the extension of our will through our creations. This is the path of the steel feather. Imagine a future where wings are not grown, but built. Where they are not born of D, N, A, and developmental pathways, but of carbon fiber and lightweight alloys, forged in a factory. Imagine them attached to the body, not through flesh and bone, but through a bio-integrated harness. The muscles are not sinew, but silent, powerful, micro-actuators. The feathers are not keratin, but smart materials that can change their shape in response to an electric current. And most importantly, they are controlled not by a rewired nervous system, but by a direct neural interface, a device that reads the brain's intent and translates the pure, unspoken thought of flight into the elegant, mechanical motion of the wings. You would not flap them, you would simply will them to move, just as you will your own arm to reach for a glass of water. This is the world of biomechanical engineering and cybernetics, the science of merging the living with the created. In many ways, this is a more logical path. We already build machines, airplanes, jets, rockets that fly faster, higher, and farther than any bird that has ever lived. The primary challenge has always been the interface, the connection between the clumsy, slow biology of the human body and the lightning-fast precision of the machine. But even this technological solution runs into the same fundamental wall that biological evolution does. The problem of energy. The internal furnace that powers a bird's flight is a masterpiece of metabolic efficiency. A technological solution would require an external power source, a battery or a fuel cell of some kind. This power pack would need to be incredibly small, incredibly lightweight, and yet hold a density of energy that is far, far beyond anything our current technology can produce. To power a human-sized pair of mechanical wings for any sustained period would require a battery with the energy output of a sports car, yet the weight of a loaf of bread. We are, at present, nowhere close to solving this fundamental challenge. But let us imagine, for a moment, that we do. We solve the interface. We solve the power source. A human being now exists with mechanical wings, powered by a synthetic heart. The philosophical question then becomes deeper than the technological one. There is an ancient paradox known as the ship of Theseus. If the hero Theseus has a ship, and over the years he replaces every single plank of wood, every sail, every rope, until no original part remains, is it still the same ship? If you replace your arms, the tools your ancestors used to build the first fires and paint the first cave walls, with mechanical wings, Are you still human? If you bypass your metabolism, the inner fire that connects you to every living thing, for a synthetic power pack, what does that make you? Where does the self, the essential quality of your humanity, end? And where does the tool begin? Perhaps this is our species' unique and strange form of evolution. We do not adapt our bodies to the environment. Instead, we adapt the environment to our will, and we build tools that become inseparable extensions of that will. The steel feather may be our truest path to the sky. But in our relentless, outward quest to conquer the air, to master the external world, are we perhaps overlooking a different kind of sky and a different kind of flight, one that we have already mastered perfectly? Now, if you feel comfortable doing so, just for a moment, close your eyes. Shut out the world of light and form around you, and turn your attention inward. Ask yourself a simple question. Where can your mind go, right now, in this very instant? Without moving a muscle, you can journey back in time to a cherished childhood memory, feeling the warmth of a summer sun that set decades ago. You can step into a favorite story and walk alongside its characters. You can soar over the crimson canyons of Mars or swim through the methane oceans of a distant moon. You can build a cathedral of impossible beauty in the landscape of your imagination. In this inner world, there are no physical laws. Gravity is not a constant, it is a choice. The speed of light is not a barrier, it is a suggestion. This is the inner sky, the boundless universe of human consciousness, and within it, you are already a creature of absolute and perfect flight. The dream of flight that we began with may not be a yearning for a physical transformation, but a reflection of a freedom we already possess. Modern neuroscience has shown us that when we vividly imagine performing an action, our brain activates many of the same neural pathways, the same clusters of neurons fire, as if we were actually performing it. To the brain, the boundary between a deeply imagined reality and the physical world can be surprisingly thin. Our consciousness is, in this sense, the ultimate flight simulator, a place where we can experience the soaring wonder of the air without the brutal constraints of physics and biology. This capacity is part of a larger gift, the gift of abstract thought, which is perhaps the defining characteristic of our species. A bird can fly, but it cannot understand the elegant mathematics of aerodynamics that govern its flight. A bird can navigate the globe, but it cannot conceive of the planet as a sphere or draw a map of its own journey. We, the grounded apes, are the only creatures on this earth who can do these things. We can understand the world far beyond the limits of our own senses. This understanding is a form of flight. Through the language of science, we can fly back to the Big Bang. Through the vessel of art, we can explore the deepest corners of the human heart. We can write stories, compose music, and paint pictures about the experience of flight that can convey the emotional truth, the soaring, transcendent joy of the act, perhaps more powerfully than the physical experience itself. There is another form of inner flight that we can all experience, a psychological state that athletes and artists and thinkers call flow. It is that magical state of being so completely and utterly absorbed in an activity that the world around you seems to fade away. Your sense of self, your ego, dissolves. The passage of time becomes distorted, hours flashing by in what feels like minutes. In these moments, whether you are solving a complex equation, painting a canvas, or simply running through a forest, you are weightless. You are no longer a body struggling with a task. You are the task itself. This is a form of mental transcendence, a kind of inner soaring where the spirit is unbound from the clumsy machinery of the body. We have spent this entire journey looking outwards, at bones and muscles and feathers, at genetics and deep time. We have yearned to break the physical bonds of gravity that tie us to the earth, but our minds are already, and have always been, magnificently, beautifully, and perfectly unbound. Perhaps the ultimate freedom we seek is not to fly through the thin air of our planet, but to fully navigate the infinite, unbounded universe of our own consciousness. And so, we return to where we started, to our grounded bodies, looking up at the sky. What is the final lesson of this long and winding journey? After so long spent soaring through the realms of possibility, feel yourself gently returning to the present moment. Feel the simple, solid, and reassuring sensation of your body being held, the gentle pressure of the surface beneath you. Feel the quiet, constant, and loving pull of the earth. We began this journey by dreaming of breaking the leash of gravity, of casting off the weight of our own bodies to float free into the air. But we have travelled far, and perhaps we can now return to this fundamental force, not as a prison, but as a cradle. Let us immerse ourselves for a moment in the profound beauty of being a terrestrial creature. Think of the smell of damp earth after a sudden rain shower, a scent that is so ancient and so deeply written into our souls. Think of the feeling of cool grass between your bare toes on a summer morning, or the rough, textured bark of a tree beneath your hand. Think of the sturdy, comforting pull that holds the oceans in their basins and gives the rivers a direction to flow. This is the gift of gravity. It is not a cage, it is an anchor. It gives our world a structure, an up and a down, a fundamental reference point around which we can build our lives and our civilizations. It is the force that allows a seed to know which way to send its roots and which way to send its shoots. It is the silent partner in the dance of life, the steadying hand that allows for the slow, stable emergence of creatures as complex and as wonderful as ourselves. In the grand story of evolution, every adaptation is also a trade-off. There is no such thing as a free lunch in biology. To gain a new advantage, an old one must often be surrendered. The ancestors of birds, in their long journey towards the sky, traded their manipulative, grasping forelimbs for wings. They gave up the ability to hold, to carry, to build, to create complex tools. They paid for their freedom in the air with the currency of their hands. Our own evolutionary story is the story of that very same trade-off, made in the opposite direction. Our ancestors, in coming down from the trees, committed themselves to the ground. This groundedness is precisely what freed our hands. It allowed them to evolve from simple tools for locomotion into the most exquisite and versatile instruments in the known universe. It is our hands that allowed us to create the first stone tools, to control fire, to paint the first stories on cave walls. It is our hands, working in concert with our expanding brains, that allowed us to develop agriculture, to build cities, to write symphonies, and to reach for the stars. Our groundedness is not our limitation. It is the very source of our greatest strength. We are not failed birds. We are spectacularly successful primates. The universe itself, in some mysterious way, seems finely tuned for our kind of existence. The specific strength of gravity on our planet is perfect for the life that has evolved here. A little stronger, and life might have struggled to get large. A little weaker, and our precious atmosphere might have drifted away into space. We are not aliens on this planet, yearning to escape. We are its native children, perfectly and beautifully shaped by it, and for it. Our limitations, we can now see, are not our flaws. They are our most defining features. They are what make us human. To wish them away would be to wish away the very essence of ourselves. The leash of gravity, which once seemed like a chain, we can now feel as the gentle, loving hand that holds us close to the only home we have ever known. The dream of flight, perhaps, was never truly about escaping our world, but about finding a way to see it, and to see ourselves, more clearly than ever before. Look up at the sky one last time. In your mind's eye, or perhaps through your window, see a bird. See it as it hangs upon an invisible current of air, a dark shape against the pale blue or the deep velvet of the night. But see it differently now. See it not with a simple, envious yearning, but with a deep and quiet understanding. See the millions of years of evolution that hollowed out its bones, turning them into vessels of air. Feel the furious, invisible fire of its metabolism, a furnace burning at a rate that would consume us. Hear the impossibly fast drumbeat of its heart, a rhythm of life lived at a different and more frantic tempo. See the world through its eyes, a world of ultraviolet colours and breathtaking clarity, a three-dimensional landscape of currents and possibilities. To see a bird now is to understand the sheer, breathtaking miracle of its existence, the 1,000,000-to-1 chances, the countless deaths and struggles that culminated in that one, perfect, effortless glide. We have journeyed through the architecture of the air, the the blueprint of the body, and the vast, deep abyss of evolutionary time. And in the end, we have found our answer. Could humans evolve to fly? Through the slow, blind, and beautiful process of natural selection, the answer is almost certainly no. The chasm is too wide. Our biology has been traveling on a different road for over 300 million years. Our entire being is a masterpiece sculpted for the land. But the true value of a great question is never in the answer. It is in the journey that the question inspires. In asking how we might fly, we have learned about the physics of the air, the anatomy of bone and muscle, the intricate dance of genetics, and the humbling scale of deep time. We have been forced to look at our own bodies, our own history, and our own place in the universe with new eyes. In trying to understand what it means to be a bird, we have, in the end, learned more about what it means to be a human. And we have discovered a beautiful, final truth. We have found our own way to fly. It is our unique and special form of flight, born not of flesh and feather, but of curiosity, of intellect, of relentless, unstoppable imagination. We looked at the birds, and we did not just dream. We studied. We learned. We understood the principles of lift and drag. Our hands, the very hands that groundedness gave us, built machines of wood and canvas, and then of steel and titanium. We created our own wings. And with them, we have soared higher, faster, and farther than any bird ever could. We have crossed oceans in a matter of hours, and we have even slipped the surly bonds of Earth entirely, leaving the atmosphere behind to walk on the surface of the moon. This is our flight. It is the flight of the mind. The dream of flight is a beautiful and essential paradox. It is our very groundedness that gives us the stability and the perspective to dream of the sky. And it is our minds, not our muscles, that are our ultimate gift for reaching it. We are the grounded dreamers. Our feet are planted firmly on the earth, and it is from this firm foundation that we are able to turn our gaze and our ambition forever towards the stars. Thank you for joining me on this gentle journey tonight. I hope it has brought you some comfort, some wonder, and perhaps a new appreciation for the miracle of your own unique existence. If you have enjoyed our time together, please consider liking this video and subscribing for more soothing stories. And please, do feel free to leave a comment, sharing any dreams this journey may have inspired. May your rest be deep, and your own dreams be filled with gentle and effortless flight. Sleep well.